Okay, hello everyone. Thank you for coming, and welcome to the Microsoft AI and ArcGIS Scalable GeoAI in the cloud. And I am really thrilled about this session because we are going to show different applications of ArcGIS working with Microsoft AI components. And this actually has some history. So maybe you remember from the last user conference, we have shown the kind of work we have done using deep learning to produce high-resolution line classification for the Chesapeake Bay. And today we have another example, which is the accidents prediction, and another example, which is the blight detection as well. So my name is Omar. I'm the practice lead of AI and machine learning at Esri. Today we have Daniel Wilson, senior machine learning engineer in Esri, Mariel from Microsoft, senior data scientist, Chris from Esri, managing the blight detection, and Sanjeev from Microsoft as well. So we want to show you today the different applications of using Microsoft different AI components like CNTK, Azure Machine Learning, and the Custom Vision Service together with different ArcGIS components like ArcGIS Pro, ArcGIS Enterprise Server, and the photo survey application. In fact, there are tremendous applications, but we believe that this combination of Raster AI, Vector AI, and Operational AI is summarizing the different kind of work that we can all do with different AI pieces together with ArcGIS. So I think I've talked a lot actually in the last days, so I'll stop talking and let my colleagues talk. But in a nutshell, actually, we're going to proceed first with using deep learning, CNTK, with ArcGIS Pro to have high-resolution line classification. Mary is going to do this demo, and she's going to demonstrate the new GeoAI virtual machine. So that was the new data science virtual machine announced today. It has the different Microsoft AI components plus ArcGIS Pro all in one box on Azure. And I really invite you all to go to the Azure Marketplace, play with this machine. It has like 3 weeks trial, and you can bring your own license for Pro. So that will be the first part. The second part will be Daniel Wilson demonstrating the accidents prediction demo that I think many of you guys have seen in the plenary, but we're gonna go deeply in the weeds, like the code and the different pieces that we have done. And finally, Chris and Sanjeev are going to demonstrate the blight detection application using photo survey with Microsoft Azure Custom Vision Service. So, Mary, welcome. Please go ahead.
All right, thanks, Omar. How's the volume on that? Should I move that down a bit? Okay, great. So yeah, I'm excited to share with you today how Microsoft and Esri have been helping the Chesapeake Conservancy, a nonprofit in the northeastern US, create a land cover map. So the Conservancy is concerned with this region of over 165,000 square kilometers in size, shown here in green. And one of their major initiatives has been to produce a land cover map, where they assign to every square meter in that region a label such as grass, trees, impervious surface, water, and so on. And that's in extensive use already by environmental scientists and conservation efforts in the region. But the problem is that in order to study some processes like deforestation and urbanization, they actually need land cover maps at multiple time points. And right now, the process that they use to create that land cover map is so onerous that that's actually limiting how often they can release this. So one part of the problem is that they're using multiple data sets, some of which are produced at the state, county, or city level, so things like LiDAR or leaf-off imaging. Another problem is that they found that the rule-based classifier that they originally used to assign labels to each square meter in this region is not accurate enough for their needs, so they've had to go through and do a lot of manual curation on those labels and post-processing, and all of that adds additional time. So what we're proposing to do and have already done with Chesapeake Conservancy is to create a neural network model that can cheaply and quickly produce those labels so that they're able to analyze multiple time points, at least at a certain quality level. Right? So what that neural network does is it takes as input a aerial image of a region at 1 meter resolution, like the one that's shown here. And it returns labels for a subset in the center, where we have the highest quality of label, like the colorized result that you see here for grass, trees, and impervious surface. So this is the type of result we're getting out of our neural network. Many of you may not be familiar with neural networks. I'm not sure if that's something that you use in day-to-day work, but the type of neural network that we're using in this case is a semantic segmentation model architecture called a UNet. And if it isn't familiar, I can just give some basic intuition on why we've chosen that model type. In order to make predictions for each pixel, we'd like to know the raw values for the red, green, blue, and in our case we also have near infrared channels in that image. But we'd also like to have some features that are based on values from the neighborhood around that pixel. So to give some context on those values, so that black might represent, obviously, asphalt or merely a shadow from something else, right? So to get that kind of information, if we were producing those, features for the neighborhood by hand, we might consider applying a convolution to do things like, do an edge detection, maybe calculate a maximum or average value for a region in these different channels, right? But the value of using a neural network model is that we can learn which features are actually valuable. We don't have to create them by hand and learn through trial and error ourselves which filters will be the most worthwhile for those convolutional layers. So that's, once we've got that convolution applied, unfortunately that will change the size of the image resulting from the convolution. And so then if we want to be able to stack it back up with our red, green, blue, and near infrared values, we have to perform a deconvolution. That's what that slightly upward pointing arrow in this diagram is showing. In order to have something in the same dimensions that we can combine together and make our final predictions from. So that's the basic idea behind a UNet. And in practice, it's found that by applying multiple convolutional layers, we can learn more complex featurization from our models. And you can start to see when we have many of these things why this is called a UNet, right? So quite deep. But this is an architecture that had already been described that we're just applying to a new use case, right? So how do we train a neural network model like this? Many of you may have heard that these networks require a lot of input data and a lot of training time. It makes sense because there are so many parameters to be fitted to this model, right? There are so many convolutional filters here. And so ultimately to do this, we'll be moving to a GPU cluster using a service called Azure Batch AI. But first, in our development process, we started with a single machine, of course, and a subset of the available data, just to test out, our training code. And so I'm going to move over and show you actually a tutorial that we're about to that we have released, showing how you can train that model. So I'm going to switch over now to my GeoAI DSVM. Omar reminded you briefly about what this is, but so this is a data science virtual machine. This is a product that we've had on Azure for quite a while now that includes a bunch of features that are useful in general to data scientists and developers. So things like IDEs like Visual Studio Code, RStudio. We have Python and R pre-installed. Some of the modifications that we've made to make this more useful for geospatial analytics include like adding ArcGIS Pro so that it's ready to go. You just come in and log in with your license information and it's ready to run. Oh, sorry, is it not showing? Oh, thank you. So ArcGIS Pro is ready to run. Python and R that were already installed. Now we've added a bunch of packages that may be a little, painful to install, a lot like Google, Proj4, Basemap, and so on. All right, hope you can still hear me. Okay, so the packages have become pre-installed, so you're available to get. They're available so you can get started working right away as soon as you provision this VM. And if you're a data scientist, you might also appreciate that we have Jupyter Notebook Server ready to run. Now you can see there's an icon here on the desktop. I've actually already loaded this thing up. And because the GeoAI DSVM is derived from a more general data science product, we have a lot of sample notebooks available on this VM type that, for all sorts of data science purposes, but we've added in, of course, specific examples for geospatial analytics. And one of them is a set of notebooks. That's not good. Okay, a set of notebooks specific to the Chesapeake Conservancy use case. And these have also been released online in a GitHub repo, so if you prefer to run them locally, you can. But there are some major advantages to running them here. In particular, all of those packages being pre-installed and the versioning under control. We can keep this a fairly simple example as a result. So loading up this first notebook, you'll see kind of the outline of what we have available. We have a notebook to show how to train this model from scratch. It's going to bring in some sample data, run for one epoch. You could, of course, run it for longer or bring in data of your own. Then we're going to apply that trained model to a new image, a static image on disk. So that'll show you the Python code behind the process for that. And finally, we're going to show you how, once you have that, with that trained model, you can bring it into ArcGIS Pro, and instead of looking at, applying the model to a static image, you can apply it in real time and see the results show up inside of ArcGIS Pro, maybe alongside the original aerial image for your comparison. Okay, so let's take a look at that training notebook. So you see the first step is that it's going to bring a bunch of files down locally. This includes the script that's going to actually perform the training and the sample imagery that we're providing. We're sharing here about 8 gigabytes of data. I think it works out to be 8 or 9 file pairs. As common in geospatial analytics, these are very large image files. Then we check that if you don't have a GeoAI DSVM, we have a list of packages here that we recommend that you install and some recommendations on how to do that as painlessly as possible. But then we move on to performing the training. Now the GeoAI data science virtual machine can be created with without a GPU, but we of course for this demo training a neural network we recommend that. It'll speed up the training. And you can create it with 1, 2, or 4 GPUs. If you do decide to create more than one GPU, we'll show you how to do distributed training and actually see the speed up that results from having multiple GPUs to spread that process across. So this will show you how that's done and help you launch the training job. We use MPI to coordinate between multiple workers if we're training using multiple GPUs. But I'll show you briefly the script here, and although I'm not going to point out many features in this script, I will say it's available here for you to adapt for your own purposes. There are several features here that probably will be useful for many other use cases in training neural networks for geospatial analytics. Most deep learning frameworks aren't built to handle very large input image files. They'll make assumptions like the idea that they can load an image from disk, crop it once, and then drop it from memory and repeat. It doesn't work very well when your images are over a gig in size. Right? So we have some things here to help with that. Also to deal with class imbalance, which is very common. So you'll see some examples for this script, and some of them are described actually in the Jupyter Notebook itself further down. So we're going to talk a little bit about what the data type is, what labels we have here, and what the training script does. So you can see if you're not familiar with the Jupyter Notebooks previously, this is the benefit. We have some code samples interspersed with a lot of description of what's happening that we hope will make it more useful to you. Okay, so once we've got that model trained, we have a second notebook to apply it to static images. You can see that here we have a little bit more of the code samples because we're not running a script externally through MPI. We're going to load the model and the evaluation image, so an image that wasn't seen during training, so we get a fair representation of how the model would perform on new data. And because we're dealing with a geospatial image, we might be interested in a specific point, right, that we could, of interest. We might want to pull out rows and columns around that point. And so we use information in the geospatial headers, I guess for these TIFF files, to find the relevant regions and extract them out. So we show the code for that. So because this model has a fixed input and output size, you might find that it's not large enough for an entire region of interest for you. And in that case, we use a tiling strategy to apply the model across the full region. So we have code illustrating how that is done. And finally, we show you how to take a look at the results. So this is the image that we're going to be predicting on. You can see the shape of the streets there. So we have a strategy for colorizing the examples, of course. This is the predictions that come out of our model after only one epoch of training. So not too splendid, right? But we're training with a subset of the data, so we're not seeing a lot of variety in the images that we provide. And we're only training for one epoch. It's typical to train for hundreds of epochs or even thousands when training a neural network model. So just to give you some concept, this would be what the ground truth labels might look like. So the script goes on to provide some information on how you could create a visual overlay so that it's easier to evaluate how well the model's working, or to actually do so quantitatively, right? A couple different metrics for that. But we often find that it's easiest to experience this by moving through a region, scrolling through a region with the aerial imagery visible alongside our predictions, and that's where ArcGIS Pro comes in. So our last notebook here would take you through the steps of how to reproduce a scene inside of ArcGIS Pro, but here I've already got that done for you. So we'll take a quick look here. And so what you're going to notice on upper left is the aerial image. At upper right, these are the land cover labels that Chesapeake Conservancy provided to us to help us train our model. And then along the bottom here, we have two different representations of the output from the model. One is our colorized best guess for every pixel. That's at bottom right. And the other is sort of a blended color that reflects the model's own uncertainty when it assigns a label. And so this is something where we can, it's been arranged so that it, we can scroll through this region. And I apologize, some of it might just be the internet connection here, but you should be able to see some of these, labels propagating as we scroll out of the region that's been buffered and filled in, right? So there are some mistakes being made here, like shadows, cold regions being identified as water, but this is this type of result that we see after a few rounds of training. Okay, so I mentioned that once we're happy with debugging our training method locally on a single machine, we're ready to scale up and train on a GPU cluster, and for that we use Azure Batch AI, which is a service that will help you create a cluster of GPUs, submit jobs to it, so it's a job manager. You could maybe queue up jobs to run overnight, and they'll manage the outputs that are created, and eventually allow you to shut that GPU cluster down. And so it's a valuable tool. You don't actually pay anything in addition to the cost of the VMs that you're provisioning, so it's free in a sense. When you're done with your VMs, you can shut them down, so you're not paying for them when they're lying idle. Very handy. So this is the GitHub repo that I hope to direct you to later. So this is github.com/Azure/pixel level LAN classification with underscores in between. And so here you'll find the Jupyter notebooks that I showed you just a moment ago, but you'll also find all of the instructions for using Batch AI. And we've tried to pair them up as well as we possibly can. So same training script, same example training data. It's just showing you the differences between how you would do it locally and how you would do it on this Batch AI service. And the one thing that I really want to call your attention to here is the section on the performance gains that we got from scaling up using multiple GPUs. So we have a few ways that has helped us. So the first is that so we're using a data parallel distributed training, which means that we take all of our available training images, which in this case is about 1,000 images, around 1.6 terabytes of data, and we partition those up according to how many GPUs we have, and assign each set of images to one GPU. So they're going to load those into memory and use those to find training examples and update all parameters on the model. After a mini batch, so a small group of images are processed, all of the GPUs communicate with one another to share their updates and arrive at a consensus model. Okay. So what we would expect is that if we add more, twice as many GPUs, we should find that the training time per epoch goes down by half. Right? That would be the ideal situation. What we actually see is pretty comparable, but not quite there. So if we had that inverse relationship, we'd have a power law coefficient of -1. We see negative 0.8. But it's actually quite good in the range where we see this nonlinearity. So after we've added, say, 64 GPUs, we're down by about a factor of 40 in the runtime per epoch. Then we lose a little bit of that benefit because we start to have delays due to communication between workers and so on. This is the type of strategy that we've used here to parallelize. There would be other options, of course. So even in that range where we're not seeing significant speedups by adding more GPUs in terms of average epoch duration, we actually do have a major benefit from having more GPUs. And that's that by the time we're up to around 148 GPUs, we can get that entire data set into memory. So we only have one data load from disk at the beginning of training, and then we never have to access, perform data I/O from a central file server again. And that means that, especially in the case where we're doing hundreds of epochs of training, that's an exceptionally valuable speed up for us. So I recommend considering that if you're in this situation in the future. So you'll see some instructions in this repo for both training locally on one machine and scaling up to train on a GPU cluster. I really hope you give this GeoAI data science virtual machine a shot, and Azure Batch AI as well. Happy to take your questions, I guess now or after the talk?
After the whole
Okay, after the whole session. But yeah, thank you.
Thank you, Mary, so much. And yeah, I second Mary's opinion. If you guys can go to Azure Marketplace and search for the GeoAI Data Science Virtual Machine, everything is in one box. Like the needed infrastructure, the GPUs for scaling, the different AI components, whether open source components like TensorFlow, scikit-learn and others, or CNTK, the other data wrangling and data ingestion kind of components, together with ArcGIS Pro. And we have configured the environment of the GeoAI virtual machine so that it has one common Python environment and one common R environment. So the R bridge from ArcGIS Pro can talk seamlessly to the Microsoft R server if you write R, and the Python, you can use the same Python code actually to access through ArcPy different ArcGIS functionalities and different kind of machine learning functionalities in scikit-learn and others as well. So now we're going to move to another demo, which is the accidents prediction. I just have a quick question. So how many of you guys have seen the accidents prediction demo today in the plenary? Okay, interesting. So what we're going to do right now is that we are going to dig deeper in the whole story, specifically in the Azure Machine Learning part, right? So we have covered that part really quickly in the plenary. So now we want to really see in action what are the different components in that part. And I think you guys can see on the screen the predicting accidents probability right now. Yep, awesome. So for those who didn't attend, just really quickly what we're trying to do, we're trying to predict the accident probability per road segment per hour in Utah. And when we have thought about this, we have seen that there are many variables that could cause an accident at first place, like weather features, time features like time of the day of the week, or spatial features like proximity to intersections or the degree of work curvature or others. So we have tens of variables in a large data set, like 7 years of data, 400,000 accidents, 500,000 segments. And it's nearly impossible for any human to analyze this manually and even predict. So what we're going to do is that we're going to use ArcGIS Pro together with Azure Machine Learning to build a predictive model that predicts the probability of accidents per segment per hour. And basically, this is the very architecture that we're going to use. We're going to develop the model using ArcGIS Pro to develop the training data set, pass it to Azure Machine Learning to build a machine learning model, and then deploy the model on a Kubernetes cluster using Azure Cloud Services, and have ArcGIS Enterprise on Azure communicate directly with the model through Python API, invoking the model every hour to retrieve predictions and display it on a map. So that's pretty much what we're going to see. And now with Daniel.
Made a mistake. Just by show of hands, how many of you are data scientists or work with machine learning on a daily basis? All right, so just a few of you. Okay, so I'm going to go ahead and start this out by showing Jupyter Notebooks. So Mary showed running CNTK in Jupyter Notebooks. One of the very common applications of it is exploratory data analysis. The first thing we had to do when we started developing the solution was figuring out what we needed to look at. So here's an exploratory data analysis of the actual accidents. So we're loading the data. This is just before we even get into any of the geospatial stuff. We wanted to look at kind of summaries over time. So this is a calendar plot, kind of shows hotspots, day of the weeks, months of the year, and different years. And this gives us a pretty good idea of where we might be looking for some of the temporal features in the data. We can also look at the weekly trends by hour, by day of the week, month of the year, hour of the day, all of that. And that gives us an idea that, hey, maybe we want to look for, we want to use the hour of the day as a feature because we can see definite peaks, 7 a.m., 8 a.m., 3, 4, and 5. But that's not the whole story. That's just the temporal features. If we do the data preparation in ArcGIS Pro, it gives us the ability to look at a whole bunch of different data sets and potential ways that they could influence accidents. On the upper left, we just see the road network and these the collision data that we have. We have average daily traffic. We have intersections. It's commonly known that a lot of accidents happen in proximity to intersections. So that's one of the features that we add to the model. Weather is obviously a very important feature in predicting accidents. If the road's icy, cars are a lot more likely to slip. And then there's other features that are going to become more important in inclement weather, such as the road curvature. If there's a curvy road, it's icy, you'd expect more cars to slide out if they take a turn too fast. And then we wanted to look at aspects like distracted driving. So we included proximity to road billboards, which are obviously in kind of the higher volume areas because you want to have a lot of advertisement exposure. So we want to see if that affects the volume of accidents that we have compared to other areas. So the actual data preparation work, we kind of explored with ArcGIS Pro, but we used ArcPy to actually prepare the data set. We create a file database so that we can store all of the relevant data. Most of the data that we have is stored remotely on various servers from the Utah Department of Transportation and others. So we basically do all of our geoprocessing here. Some of this includes calculating features like the road curvature. We use sinuosity as the metric for road curvature. And then we go finally to joining the weather data to the roads and the actual accidents. Once we have the data in properly formatted in the geospatial formats, the next step is to bring it into a format that we can use for performing machine learning. Right here, we're just doing some basic feature extraction. This notebook goes through all of the preparation work, including joining up the weather data to the individual accident samples, as well as an important thing that I just want to spend a minute on. We have a record of roughly 400,000 accidents that happened over the last 7 years. But to train a machine learning model, what we need is both positive and negative examples. What we want to do is predict the probability that we're going to have a car accident on any given road segment per hour. We need examples of when there weren't accidents so that the model can learn what the difference between when we see an accident is and when we don't. So we actually write this big routine that takes samples out of all of those positive accidents and samples times where accidents didn't occur that are at either similar road segments, similar times of day, or similar days of the year. So we have a whole bunch of counterexamples to when these accidents occurred that are very similar to situations where accidents occur, and that allows the model to focus on those important details. Once we have all of that completed, we actually just dump the data file out in a big comma-separated values file, which we can then upload to Azure Blob Storage. So this way, the data is stored in the same data center as our virtual machines where we're actually going to train the data on. And then we can also deploy any models to that same area and have the data co-located. So now I'm going to jump into Machine Learning Workbench. Once the data is in Azure Blob Storage, we can directly import the data into Machine Learning Workbench, which gives us the ability to do some basic data manipulations. We can, for example, we can remove columns, we can create histograms or scatter plots, various exploratory data analysis, across this training set that we prepared. So right here I have a histogram over hours that you saw previously in that Jupyter notebook, and statistics about the temperature so we can kind of get the general idea of the features that we're looking at. This is really convenient because we can create an entire data preparation workflow, including removing null values, removing columns we don't care about, all sorts of stuff like that, so that when we actually get to the training routine, which is just a simple Python script, we can use the data preparation file that we created before. All of that gets loaded directly by Azure Machine Learning through this single line of code here on line 47 that shows we're taking that data preparation file, and it's being loaded directly into a pandas data frame. If you work with pandas before, it's a very convenient data structure for working with tabular data in memory in Python. So the rest of this file, what we're doing is we're selecting the features that we care about, doing some rescaling and some transformation so that all the data is in the right format for the model. And then we define some parameters for the actual algorithm we're using. In this case, we're using an algorithm called gradient boosting. It works very well on a mixture of categorical data and kind of continuous data. And we take our input features, which were the examples of when accidents occur, when accidents didn't occur. We split that into two sets, 90% that we're going to train the model on, and 10% that we're going to evaluate the model against. We run this model with 200 rounds of iterations, and then what we do is we watch for the accuracy of the model to stop decreasing, and it'll actually start increasing on our evaluation set, and that gets us to the point where the model is best trained against the data. Azure Machine Learning makes it very easy to kind of monitor these the various metrics, such as the accuracy of the model, precision, recall, area under the ROC curve, as well as plots. So we can save off plots that evaluate that particular run. So if I look at, hold on. There we go. So if I look at this is a record of previous runs. You can see I have a lot of failures. Omar didn't want to talk about that in the keynote, but I spent a lot of time learning how to do this machine learning Workbench stuff over the last couple weeks. So after we had all these failures, we had a lot of success, and it's actually pretty easy to work with overall.
Maybe we need to inquire if there is a way to delete the failures. Right? We actually Googled this today, but we failed to do that.
So here is a log of various runs that succeeded. Here's metrics, performance evaluation of the model that I ran. You can see I had, for a lot of these, I had some pretty high test accuracy. For this run, I had a lot lower. But what I was actually trying to do for that run was maximize recall, which is a metric of how many of the accidents we are predicting. So I wanted to say, let's try to predict as many as we can so that we can generate an accurate risk map. If I look at the details of this run of this training file, this gives us the metrics for that specific run. I can look at output files from the model, and for some reason this isn't loaded. There we go. So this is the actual model file that we're saving off, as well as visualizations of performance.
Yeah, I just have a quick note here. I mean, this feature is really important. So when we were developing that model, there were daily discussions between me and Daniel about what did right, what did wrong, why did we have this kind of precision rate, and now we have different precision rate. So having an easy way to track the different iterations and the different kind of stats for every iteration is really convenient to track our progress and understand why our performance differs through different techniques. Yeah.
Once we have the trained model, we can use Machine Learning Workbench to create a scoring file. So this is what we're actually going to use to deploy the service and run it in the cloud at scale. It makes it really easy to do this. So it's a lot of work to stand up a REST API and interface that with machine learning library, get everything running, and have it able to scale all at once. But with Machine Learning Workbench and the machine learning tools, it makes it a few lines in the command line and a very simple workflow. So this file can either be developed here. You can also export it into the PyCharm or Visual Studio's IDEs to do development. You get a very nice template when you initialize your project. So you don't have to write all of this code. You just have to fill in the gaps for what you need to do to evaluate your model. In this case, what you need to do to develop the REST API is implement this generate API schema function. You have to do model initialization, so that's just loading your model from whatever file you saved it to, and then running. And run is where all the actual evaluation of your model happens, where you're testing it against new data. In this case, we're using the ArcGIS Python API to load data from ArcGIS Enterprise, perform processing in memory against the model that I had trained before, and then we export the data back to the processing tool. Once you have your model deployed, you can actually put that in a Kubernetes cluster service. So Azure Cloud Services allows you to scale up and deploy a Kubernetes cluster to run your model. Once you have the model file written, you create a Docker image, run that on the ACS service, and then you can scale that up as needed based on the amount of users and connections you're having, or you can change the actual allocation of the CPUs and memory that you need for your model. So that's how you develop and train a model, deploy the model in Azure Machine Learning. What I'm going to show you now is a couple examples of this. This is all done in the entire state of Utah, but we're going to focus on a couple of examples in the Salt Lake City area right now. So right here in Bountiful, Woods Cross area, you can see here's the road network. And if I turn on the accidents prediction layer, you can see that along some of these major highways, we're predicting some higher risk spots for accidents. There's a couple that aren't on the major highways as well. The color scale here is green is we're just calling low risk, yellow is medium risk, and red is high risk. And then I'm going to turn on the accidents that actually occurred on that day. They're going to show up eventually. There we go. So you can see we're doing pretty well. For the most part, we're predicting these accidents occurring. You can see that they're happening a lot of times on these red segments, yellow segments. And I'm going to zoom in on a particular example here. Oh, that's not it. Do you remember where that one was, Omar? Oh, there we go. So here's an example of an accident that occurred on Curvy Road. So this segment, based on its proximity to intersections or near other features, was determined to be higher risk, and we think that road curvature, had something to do with that part. Here's another area. So this is South Salt Lake City. I'm going to turn on the accident predictions, so you can see again mostly major roads, highways, but then some side roads as well. And these are the actual accidents that occurred. So if we look at the ones that happened on highways, a lot of those make sense. A lot of them are happening near exits or curvier sections of the highway. And a lot of them are happening near intersections as well, as predicted by the model. And then finally, there's one more example here. Here's the predicted risk. And these are the areas where the accidents actually happened for that day. So, what we've shown you is how you can develop and prepare your model or your data in ArcGIS Pro and using the ArcPy API. Azure Machine Learning Workbench makes it really easy to develop the model and deploy it. And then the results can easily be published in ArcGIS Enterprise, ArcGIS Online for further visualization. Thank you.
Awesome. Thank you, Dan. Yep. So one thing to mention is that these maps you guys are seeing are basically reading data from ArcGIS Enterprise. So just to summarize, we have used Pro to prepare our training data set, pass the data to Azure Machine Learning to train the model. Then once we have a trained model, we want to take this into production. So we deploy the model into a Kubernetes cluster using Azure Cloud Services. And once the model is in production, it will need continuous stream of data to be fed to it to produce these predictions, right? And these streams are usually geospatial streams, and hence the need for ArcGIS Enterprise on Azure to be sitting at the same Azure environment so that we have the data, the model, and the analysis all running in the cloud in the same Azure environment. And we have built a geo-processing service that acts as a web tool that can either on hourly basis invoke the model to get hourly information products or dynamically as per need. And once we have Azure ArcGIS Enterprise in this kind of solution, it allows for enterprise scale. So you can have the system of engagement, people accessing this feature service of predictions, building custom applications, extending the functionality through Python API, doing big data analysis using geoanalytics, and the list goes on, right? So that's the power of using the GeoAI virtual machine together with ArcGIS Enterprise all on Azure. And now we're going to shift to another example, a really interesting example for using the Custom Vision Service of Azure with the photo survey. Thank you.
Thanks, Omar. Everybody hear me okay? Okay. My name is Chris Pascalia, and I work on the local government solutions team. And today I want to talk a little bit about a project we're working on. It's actually a prototype, and you'll be able to get it today if you want it. So we'll talk about that towards the end. But it's really about predicting neighborhood blight and doing kind of focused property condition surveys. So we've been doing a lot of work with neighborhood stabilization. One of the applications that we've developed is called Photo Survey. And why it's important is really about inventorying blighted properties to devise neighborhood revitalization efforts or conducting rapid damage assessments in your community, or even targeting reappraisal efforts for property valuation, even identifying structures that pose health concerns for folks. So those are the kind of the main workflows around what photo survey is. And what we've seen is a lot of cities actually go and hire people to go out in the field and perform door-to-door surveys for property condition. So you can see a few examples here. We have the Gary, Indiana property survey, the City of New Orleans property survey, Motor City Mapping, which is a project in Detroit, to basically go out to every property within the city and perform a very focused property condition survey. And what we did was we actually partnered with the City of New Orleans on this project. And what the City of New Orleans wanted to do was really just kind of expedite that process. How can we go in the field quickly, take street-level photos, and then use those in a very focused property condition survey application? So you can see here we're visiting with the city, and the city's actually mounting a custom camera they developed to do this street-level photo collection. And then what we did was work with them on the photo survey application and the workflow to help you process those images. So there's some challenges with that, right? We wanted to use standard devices that any city could go out and purchase. So you can see that as a challenge. Also, we wanted to provide a very focused property survey application that would expedite that property condition survey. We wanted to randomize the properties across the city. So the City of New Orleans wanted to make sure they had an unbiased survey of those properties. And then provide a bunch of useful reports and map-based reports on the back end so you can actually operationalize that condition survey and send folks out in the field to work on those issues. So here's just some available cameras that we tried out and used as part of the solution. We also give you best practices on what cameras that you could use to do this street level photo collection. And this was the initial photo survey application. It's an application you can get right now. It's available on our solution website, and it helps you do this very focused property condition survey. So you're seeing just the photos of the property. You might see multiple photos of the property based on the location of those photographs. And then on the right-hand side, you see a very focused property condition survey that can be tailored for your city's survey. So those are just simple questions. The reason why we wanted to work with Microsoft is could we make this even easier for cities and even make it faster to do these condition surveys? So in this slide, you actually see a diagram of how we worked with Microsoft on this next generation of what photo survey is. So on the left-hand side of this diagram, you see a vehicle with a camera mounted driving around the city. We offer some tools inside of Pro that help you process those street-level images and then publish them to a service which the photo survey application uses, but also Microsoft. And then we connected to Microsoft's Custom Vision Service to process the images before the condition survey is even done. So you'll see that, and I'll show that in a little bit. Out the other end are a bunch of map-based reports, like I mentioned. There's even a dashboard to kind of help you review the results of that probability, blight probability. And then you can operationalize folks within your organization with things like ArcGIS Collector and Workforce to take that to the next step and actually get folks in the field, taking care of those problems, if it be with policy or other methods. So without further ado, we'll just go ahead and jump out to a demo. So I want to start the demonstration in ArcGIS Pro. And what you're seeing here in the map is just all of the photo survey points collected street level. So you're just seeing points on the map, essentially. Each one of those points has a related set of images for that property condition survey. We have the tools that help you process the photos. So as long as the photo has a location, we'll actually take that photograph, take the location from it, and then assign it to the nearest property based on proximity. And there might actually be multiple photos per property, which is something that we also wanted to make sure we had, so that if there's any obstructions in the street, then we can actually scroll to the next photo and see the property and do the property condition survey. So we offer some tools inside of Pro that are available right now to help you process the images. And then we have a new prototype application that connects up to Custom Vision. And we're actually, I'll crack that tool open and show you what that looks like. It accepts the photo survey points layer that was processed. And then you can actually go in and say what category of blight that you want to actually go in and try to predict. So for instance, we picked a few just to start. One of them was overgrown yards or overgrown properties. The next was properties that had graffiti and properties that are boarded. So those are kind of the three indicators of blight within a neighborhood. There's other indicators as well, and we're working on those, kind of testing out the models and making sure that they can actually predict those things. But these are the three we started with. So overgrowth, graffiti, and boarded windows and doors. And then the next thing it requires is just a custom vision training key information from Azure. So as long as you have Azure and you can connect to custom vision, we're providing all of the photographs as a baseline for the property condition survey. And I'll talk about that here in a little bit, but we're actually sharing those photographs on GitHub. And those are the photos that you can use for your baseline blight probability score. And so I'll talk about that here in a little bit. So those are the tools inside of Pro, fairly straightforward. We're also, Ryan's actually in the front row here. He's been helping out with the tools. We actually have another tool that will help you train the model, so you don't actually have to do that manually as well. So there's another tool we're working on inside of Pro to make that even easier. So you just grab the photos from Esri, the ones we provide. You use those to train your model and then predict blight from that. All right, so those are the tools inside of Pro. What I'm going to do now is show you the end result of the analysis. So what you're seeing here is operations dashboard, and you can see those three categories that we've added to our model, one for graffiti, one for overgrowth, and one for boarded windows and doors. And you're seeing every property that is the highest probability of those things. So this is at anything over 60% probability of overgrowth, boarded windows, or graffiti. And what I can do is I can click on individual properties. You can see the probability score changes based on the actual property I click on. And what I can do is actually click on the map, and what that's going to do is bring up the actual property photograph. Hopefully you guys can see that on the screen. So you can look at it, see if it makes sense, and then you can see obviously here there's some overgrowth in the photo, and it's giving you a general probability score for that property. So that's just really a dashboard kind of showing you where these things might be within the city or community. And I can also take an average composite score of all those things and look at the probability of blight using those three categories. So this is just kind of a heat map showing you where concentrations of this might occur in your city or county or community. So that's the probability dashboard. I did talk about workforce a little bit. So how do I actually go now and interrogate those properties on the ground? This is where workforce for ArcGIS comes in. Now I can actually operationalize staff to go in the field and actually do that very focused property survey. That could be with Collector or Survey 123 even. Or you could even take the results of that dashboard and just queue up the photo survey application to do that very focused survey only on the properties that had high probability scores of blight. So that's the idea there. The last thing I wanted to show briefly is where you can get this right now. So this is our GitHub repository for photo survey. And we've just included those blight prediction model photographs in this GitHub repo, as well with the tools that Ryan and I are working on to kind of help you predict blight if you want to take a look at them right away. We also want this to be a collaborative effort, so if you have photos of your own that you've collected for your city, let us know. We can add them to the models if you let us, and we can actually use those to improve the models over time. So that's one of the things we want to do as part of this project is have this collaborative effort, lots of cities participating and helping us make those models better to help predict blight. And that's the idea there.
Fantastic. Thank you so much. Thanks. Thanks. Sanjeev, do you want to add anything?
Hey folks, so my name is Sanjeev. I'm a developer advocate at Microsoft, and I help developers develop new applications on Microsoft platform. So first of all, let me start by asking, how many of you are not data scientists? Can I show up? Okay, so that's pretty much most of you. So a lot of the conversation focused today on, here is how data scientists can do stuff with Azure Machine Learning. And one thing that gets lost quite often is that the tooling that Microsoft has built is targeted at both sides. The data scientists can do really, really good work. And people who are not data scientists, developers such as you and me, because I'm a developer, I'm not a data scientist by trade, can still use machine learning without wrapping our heads around all the terminology and all the complexity that comes in machine learning. Like the first time I hear a CNN, DNN, convolution, neural network, my brain starts overheating, and I don't really want to understand all of that because it takes a PhD to understand all of it. So the way I would actually describe this today, my goal is essentially to impart some understanding on you, like how you can, as developers, just use machine learning that Microsoft offers. So if we had to actually, let me ask another question. Let's say if I give you categories saying, are you interested in images, or speech, or text, or some random other stuff? What is the most interesting thing? How many people would be interested in images? And how many in speech? Like a few people, right? And text? Very few. So most of the use is around images, so I will keep it there. Keep it very, very scope to that. The way Microsoft has worked to bring image classification, the process is called image classification. What it really means is you have a bunch of images, you want to say this one contains a hydrant and this one doesn't contain a hydrant. That's all your problem is. You want to classify images, you want to figure out images that have hydrants and others that don't have hydrants. And you can build a product around that, right? Just like over here, if you could figure out if a house was boarded versus a house was not boarded, then that solves our problem. That's what we are trying to do. And the way a data scientist would do it is basically they would collect a ton of images, they would do some bunch of training, and then they would go over it again and again and again till they got something working really, really well. Of course, you and I are not data scientists, so we cannot really understand what to do there. The way Microsoft made it simpler is they took a lot of images across many, many categories. Like there are people, animals, houses, boats, God knows what. Around 10,000 images in various categories, and data scientists from Microsoft sat down and trained, whatever train means, a model around it. And in the end, something came out that if you feed it an image, it'll say, this looks like an animal, likely a horse. This looks like a house, likely a Victorian house, something like that, right? So what we have done to make your developer's life easy is that service is up and running. It's called Custom Vision. And in there, your job is to essentially go and say, this is an image of a house that has boarded windows. So you upload an image and you put a text around that saying boarded, 20 of these. And then you upload a few more images, say not boarded, not boarded, not boarded. And what Microsoft does in the background, that's all you did. You called a few REST APIs, or you went to a website and just uploaded a few images, put some tags on them. And after that, you went ahead and hit train. What's happening in the background, you don't know, you don't need to know. All that happens internally is like, there is this model that recognizes all of these various features, and you are telling it, you know what, like that model already knows what a house looks like. You are telling it, this is a house that I'm interested in because it has boarded windows, and internally tries to figure out what's the common theme in all of these images. And it'll see this little plywood in the windows or doors, and it'll say, well, that's what the common theme is. And after it is done, you can submit an image and say, hey, is this boarded or not? And it'll try to find similarities between that, what you had previously submitted, and what you just submitted. And it'll say yes or no. And the way it says yes or no is more granular. It'll say 70% yes or 90% yes. If you're somewhere like 75% and above, you can be pretty fairly confident that what you got out is very, very accurate. So that's what the Microsoft machine learning thing is. So when we worked with Chris over here, we went ahead and did exactly that. We uploaded a bunch of images of boarded houses and non-boarded houses and overgrown houses and the final one, roof damage one or whatever. And then we started submitting images saying, is this yes or is this a no? And that's what came out. You still have to be developers. You still have to understand a little bit of data science. So initially when we went, we said, can we figure out if a house is in a bad condition or not? And we just gave everything in a lump sum, like boarded houses, overgrown, and everything together. And the other houses which are in good condition, and we said, can you tell me if it's bad or good? And the machine learning model did not do a very good job. So we said, okay, how about we'll break it down? We'll say boarded, 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 and then, overgrown, overgrown, and then the third category. And can you now tell me, is this house boarded or not? And the machine learning model came back with a very good yes or no. So instead of saying good or bad, we broke the problem down and we said, check all three of these categories, and if any one of them or more than one says yes, then very high probability that is indeed a problem. So that's how we developed, and the key thing to remember there, if I had to leave a messaging, is one, it is for developers. It is available to developers, and it's available in any way that you want. You can write code directly against REST APIs. You can write code against Python APIs. That will make actually your life a little bit easier. We also have Android and iOS SDKs, so you can write code against those. And that's how we have been as Satya likes to say, Satya Nadella, our CEO, we are democratizing AI. It's not just for people who have a very good understanding of AI, but for people like you and me who just wants to use it in innovative ways. And that's it. That's my part of the presentation. If you have any questions, I'm available after the talk is over, and you can come talk to me. Thank you.
Yep. Thank you so much, Sanjeev. So anyone has any questions? Okay, I'll come bring the mic to you.
I'm from Pinellas County, Florida, and we do have mosquito control problems. And there's a great suite of apps, maps and apps already out there from Esri. But it would be great if we had something that would learn to read the color of pools from abandoned properties, so it could tell just is it blue, green, or black. We have a gambusia fish project where we'll drop from helicopter, we'll drop fish down into these pools, and it's fun unless you're the fish. And they're mosquito fish, and they'll just eat the larvae. But it would be great if we had something that we can tap into right now, or if not, can we work together on something in the future?
Sure. I mean, I see this as a perfect application of using the Custom Vision Service and possibly the photo survey. And I would definitely invite you to connect with Sanjeev and Chris after this session to know more about this and see how you can collaborate. Okay. Any other question?
My question is aimed at the motor vehicle prediction for accidents. The results you showed were very impressive as far as the predictions that you came up with for that assumed day. How accurate was it on time of day? Could you predict when an accident was going to occur on that freeway or one of those intersections?
Those predictions were by hour. So that was saying for, I think that was 3 p.m., I believe.
So that was 1 hour's worth of data?
Yeah, from 3 to 4 p.m., that was the probability that you were going to see an accident or a risk score.
Okay. Interesting. I'd like to talk to you afterwards.
Yeah.
Thank you. Yeah.
Yeah, a similar question actually regarding the land cover classification. After all the training, how accurate was your model regarding the truth?
Well, so we withheld a test set of about 30% of the images available, and in that region, it's order 80% on a per pixel level. Important to consider, the actual model that preceded it at Chesapeake Conservancy applied algorithmic segmentation first, and then applied labels to the segments. So probably the most dramatic, the most relevant comparison would be, whether we've achieved the level of accuracy that they find appropriate, by matching those labels. And unfortunately, we don't have that information yet on, how well our labels would apply if we took, say, a majority vote for each segment. And compared. So we don't have that quite yet. We're actually in the midst of redoing some of the strategy that we're using to train, and the reason for that is that we'd like to take this model nationwide. So there are certain land types that we don't see in the Chesapeake Conservancy region, right, in the Chesapeake Bay, that we'd like to be able to predict on also. And so for that, we're trying to leverage some actually lower resolution data from the National Land Cover Database and use that as a training label, even though it's not available at the 1 meter resolution we've been working with previously. So that's one of the reasons we haven't focused too strongly on improving the accuracy to a higher level on this model, is that we're actually considering a major change to it. But I hope that helps.
Thank you, Mary. I would like to add to Mary's answer that I know for some parts at Chesapeake we achieved like 91% accuracy, 91% at some parts. But yeah, as Mary mentioned, we're still working on the model to fine-tune it more. Any other questions? Okay.
Sanjeev told that we can be developers and still, learn this what it takes PhD to learn, right? So I have a very stupid, primitive questions. Typically in commercial software, we develop code, we write code, right? It's code, DLLs or whatever. And we have database schema, it's databases. And we sell them repeatedly to customers. Take empty database, write a code, fill data, apply. And about models, if you say train the Utah, and we'll say, okay, it failed a bit, but maybe we can use it in Florida, right? How much does it take to just, scale it or make a copy of it, or it should be retrained because the map will be different?
So if we are talking about custom vision, then the way it works is what they call model. Essentially, it's some sort of numbers. Essentially, it's a bunch of numbers that come out of training. You can take that and you can say, you know what, here is a model. Either you can offer as a service, in which case you can just say, hey, Florida, can you use this one? That's pretty straightforward. Or if you want to actually give them the software, then you can just take that file that contains those numbers, package it along with the software, and sell it along to the other side. So it's actually really, really straightforward. Even with custom vision, even though Microsoft runs the backend, once you have done the training, they allow you to export the model out of the service. Re-importing back is supported in limited ways right now, but it's still in preview. The service is still in preview. So hopefully by the time it reaches release, you will have the ability to re-import it in whichever way they want. So you can actually just take the model, sell it to state of Florida, and they can take it, re-import it, and just run with it. So that's a total possibility.
On different map, yeah?
Yeah. This is basically, the model has got nothing to do with map. The model essentially says, if an image comes in, and you want to figure out whether it is, for example, whether it is a dark pool or light blue pool or whichever pool, that's what comes out. So Microsoft is only concerned till that portion. You submit an image and out comes the result. How you hook it up to the maps is up to you. So you can say, I'm standing up a service which will actually showcase a map, and on the map you submit an image and it'll light up saying red. For example, that's what Chris's example was, right? So you can, sorry?
Not images, accidents. Accidents in Utah.
Sorry.
Yeah.
If this solution can be easily deployed to Florida, just feeding a different road maps, or
so
it should be retrained again according to your...
In the case of accidents prediction, I think the model will be transportable to areas with a similar climate or similar highway structure. Going from somewhere like Utah, where it snows a lot in the winter, to Florida, there's going to be a lot of different factors in Florida that one, the model doesn't take into account, and that the model is never going to see. So we're never going to see icy road. Well, I say that, but this year there are icy roads in Florida. But normally, we're not going to see icy roads in Florida. It's not really going to be a factor in the model. So in that case, the model is not going. It'll perform fine on all the features that aren't weather related, but there'll be factors that won't benefit, and we might want to include different factors for Florida.
Thank you.
Thanks. Any other question? I think I had a question. Okay.
I used to do a lot of water quality modeling, and I know one thing we struggled with a lot was, it's not working.
Okay.
I can yell. But one thing we struggled with a lot was getting beyond, I saw you had the herbaceous classification, but getting beyond that and said this is cropland, this is pasture, this is urban grass. Have you tried at all to differentiate between those with any success?
Yeah, this is actually a problem we're addressing right now as we make that switch to the National Land Cover Database. So they're making distinguishing between pasture, hay, open developed space in urban areas, so things like golf courses and land in backyards. And so what we're attempting with our model is to just leave open land types that might be filled in by different qualities within those regions. So for example, in the National Land Cover Database, you might have a label that effectively suggests that something is roughly 25 to 50% impervious land, and otherwise would be typically grass or trees. And so we can start to ask well, what if we allow that to represent some mixture of three different classes that we don't even label to be specific, and we just allow those to be trained over the course as the model is trained, then we might be able to pick these things up. I think we've yet to see whether we're going to really pick up a difference between a longer grass form like you would see in grassland or pasture hay. But yeah, we'll see eventually, I suppose.